Hi, I'm Bartek.
And I'm Pavel, and today we'll be explaining the Knuth-Morris-Pratt algorithm.
We will start off by introducing the problem of string matching and where it is used. We will then move on to explaining the partial match table algorithm, which is used by the Knuth-Morris-Pratt algorithm, later referred to as KMP. Afterwards, we will show you an example of the algorithm generating this table, followed by an example of the KMP algorithm working. We will also mention the complexity of the algorithm. Feel free to jump to the section you are interested in, as they are all independent.
What are string matching algorithms used for? Basically, these algorithms are used when we want to find an occurrence of the string in another one. One example of this is searching for the string ABC in the string DBA-BCD. There are many ways of solving this problem, however we found KMP most interesting.
You might be wondering where this might be useful, and it isn't hard to find examples where you would apply this algorithm. You could use this algorithm to find matches in DNA sequences. Every time you search for a database, the database uses string matching to efficiently find the correct result. You might have even used string matching to find this video on YouTube, since it is used in search engines. These, of course, aren't the only examples. It's also used by spell checkers, network intrusion detection systems, and language syntax checkers.
KMP uses what is called a partial match table to efficiently solve the problem. Using this method means we don't have to backtrack. The pros of using this method are that the algorithm is online, meaning it can process the data piece by piece, and we can add more data whenever we want. It only takes linear time if we already have the partial match table. It is also very good for searching multiple strings if we are searching for the same word, since we don't have to generate the partial match table every time. For instance, searching through a list of files for a file name. On the other hand, the algorithm doesn't offer a huge improvement over the average case, for instance where the alphabet size will be large. It's also bad when we have to regenerate the partial match table every time.
Before we explain KMP, we need to explain what the partial match table allows us to do. The goal of the table is to allow the algorithm not to match any character of a string we are searching through more than once. Here we see a comparison between a brute force method and KMP. As we can see, KMP uses only the first and last rows of this table, compared to brute force, which uses every row.
This is the algorithm for generating the partial match table. We'll now walk through an example of the algorithm being used for a simple string ACACBB. It is contained in the array W and the table is in array T, where each number contained within T indicates where we have to return to in the pattern. We start by assigning T of 0 to be -1 and T of 1 to be 0. This is because -1 represents the beginning of the pattern we are searching for, and if the second character is wrong, we always have to return to the starting position. We also set pos, which is the position in the table we are filling in, to be 2, because positions 0 and 1 are already filled, and rp to be 0, which is the return point if we get a mismatch. We start by making sure the while loop is satisfied. Since pos is equal to 2 and length of w is 6, we enter the loop.
W of pos minus 1 is C, and W of rp is A. Therefore, the first condition isn't satisfied. rp is 0, so the only other option is for it to execute the else statement. So we set T of pos to be 0 and increment pos. We now return to the while condition, which is satisfied, so we remain in the while loop. Now, W of pos minus 1 is equal to W of rp, since W of pos minus 1 is equal to A, and W of rp is also equal to A. We therefore increment rp, set T of pos to be equal to rp, and increment pos. The while loop condition is still satisfied, and once again we have a match. T of pos minus 1 is C, and T of rp is also C. We repeat the steps we did previously.
The condition is still satisfied. However, now W of pos minus 1 is not equal to W of rp, but the second condition is now true. So we set rp to be equal to T of rp, which is 0. As you can see, if we continue executing this algorithm, we'll eventually fill the table.
Now that we have covered how the partial match table is generated, we can proceed to the algorithm itself. As input, the algorithm takes two strings, S and W. S contains the string we are searching through, and W the word we are searching for. The algorithm will output an integer indicating the starting position of where we have found the string. It will return -1 if no match has been found. We also define T to be the array generated by the partial match table algorithm for string W.
This is the pseudocode for KMP. We will now work through a simple example showing how the algorithm works. We start by assigning variables m and I to be 0. M holds the value we want to return, and I is used for checking the characters within S, where I of 0 is the first character in W. The while condition is fulfilled, so we enter the while loop.
We find that the first condition is met because the first characters of W and S match, and the second condition is not met because we haven't found the whole string yet. So all we do is increment I. We check that the while condition still holds, and proceed to find that we don't have a match this time. So we execute the else statement, where we use a partial match table to determine the values of m and I.
The while condition is still satisfied. For the next 3 characters, the algorithm finds matches because S contains ACA and W starts with ACA. However, it now finds a mismatch, so it searches for a pattern to which it can revert to. This is made possible by the partial match table. Unfortunately, we couldn't find a pattern, so we have to start from the beginning. This time though, the algorithm finds matches all the way. Now we find that we have matched 6 characters, which is the length of W, so return m. That turns out to be the position at which we can find W in S. If we couldn't find the string, the algorithm would exit the while loop and return -1.
You might be wondering how efficient this algorithm is. In order to answer this question, we have to divide the algorithm into 2 parts. The first is pre-processing, which takes OM time, where m is the length of a string. This is because we only scan through a string once. The string matching part of the algorithm is also linear, i.e. ON, where n is the length of the string we are searching through. This is because we never go back in the string we are searching through, and the amount of time spent on checking the partial matching table is negligible. So the total time complexity is O of m plus n. And this concludes our presentation on KMP. Thank you for watching. If you have any questions or comments, please feel free to ask us in the comments section below.